So Bernoulli's equation has the same, almost the same format for, or the standard form for linear equation. So the only difference is the presence of the y raised to n. So that makes it a nonlinear differential equation. But then, so we can transform this nonlinear equation into a linear equation, so through certain substitution. So after transformation, so we are just going to use the same method for linear equation. So that's the integrating factor. So for Bernoulli's equation, so will be the same. So to better understand that, so let's proceed with our first example. So we are given xy prime plus y is equal to xy cubed. Okay, so our objective in Bernoulli's equation is to transform the equation into this format. So we will be introducing a new variable here, which is v. So thus, it will become dv, so with respect to x, plus p of x times v, so it's equals to q of x. Okay, so this is our objective here. That is to transform the given Bernoulli's equation into the standard form of a linear equation. So that one can be done. So starting, okay, so from the q of x, so we'll start with our first step is we transform the right hand side of the equation, okay, so into a function of x alone. And then afterwards, so we're going to make the substitution. So by substituting v in terms of the dependent variable, and lastly, so we ensure that our differential, so we just be the differential without any coefficient. So whether that is a constant coefficient or a variable coefficient. So to do that, so let's start with our first example. So for our first example, of course, we're going to change, so y prime, so into dy over dx, and this plus y is equals to xy cubed. So as I mentioned, so our first step is to ensure that there won't be y, okay, so there won't be y's at the right hand side. So we are to ensure that it should be a q of x. So in here, so we have xy cubed. So that's, we need to remove y cubed, okay, so to just make it as a function of x alone. So to do that, so we multiply the reciprocal for the value of y. So if we have y cubed, so its reciprocal is y raised to negative 3. So y raised to negative 3. And then we distribute it. Okay, so we distribute it to all the terms. So first, so y cubed, so times x dy over dx, so that will make it x y raised to negative 3, so dy over dx. Then afterwards, so we distribute it to y, so plus, so y raised to 1 times y raised to negative 3. So we have the same base, so we subtract the exponent, so that is 1 minus 3. So that makes it y raised to negative 2. And then lastly, so xy cubed times y raised to negative 3. So 3 minus 3 for the exponent, so that would be 0. And thus, so leaving the right hand side of the equation to be a function of x alone. So in this case, our q of x is, it's just simply of x. Okay, so we are done now with our first step. So our next step is we need to transform the differential equation or the Bernoulli's equation into a linear function, or its linear function in v. Okay, so in this case we have y raised to negative 2, okay, so which is not linear. So thus we're going to make the substitution. So that makes the Bernoulli's equation a substitution approach. So we let v, so to be equal to y raised to negative 2, because this is the reason why it is a non-linear. So v will be equal to y raised to negative 2. And then afterwards, so we have introduced a new dependent variable v here. And then of course we have the old dependent variable, which is y. And then so we're going to derive both sides with respect to x. So deriving v with respect to x, and then we're going to derive y with respect to x as well. So deriving v with respect to x, so that will lead to dv over dx. And then the derivative of y, so with respect to x, so we derive y first. So using power rule, that would make it negative 2. Then y raised to negative 2 minus 1, that would be negative 3. Then derivative of y, so with respect to x. So now, as you can see here, so this portion is the same as this. So the only difference is it has a negative 2. Okay, so it has a negative 2 attached on it. So therefore, we're multiplying the reciprocal of the entire equation, so by negative 1/2. Okay, so multiplying it by negative 1/2, so that will yield to negative 1/2. So dv over dx is equal to y raised to negative 3. So dy over dx. So negative 1/2 dv over dx is equals to y raised to negative 3 dy over dx. And now, so we can now substitute. Okay, so substituting, so I'm going to attach x here, and then bring down the y raised to negative 3 dy over dx, so which is the same as negative 1/2. So dv over dx. And then plus, so I'm going to change this one, y raised to negative 2 into a v. Okay, and that would be equal to x. So as you can see here, so we are now done, okay, so with the first step, so which is a function of x alone. And then for the second step, so we do have v now. Okay, so our last approach is to remove the coefficient of dv over dx. So in this case, so we have the negative x over 2 as the coefficient of dv over dx. So thus, we multiply it with the inverse. So that would be negative 2 all over x. So multiplying it with negative 2 all over x, so it would cancel out the negative x over 2. So giving us a dv over dx, and then minus, so negative 2 over x times v. So negative 2 all over x, multiply it with v, is equals 2. So x will be cancelled out, so leaving us to have a negative 2. So dv over dx minus 2 all over xv is equals to negative 2. As you can see now, so we were able to transform the entire equation, okay, so into a linear equation. And in here, we can now identify, so what is our p of x, so which is negative 2 all over x, so do not forget the sign. Okay, so the negative 2 all over x, and then our q of x is equivalent to negative 2. And we can now compute for our mu of x. Okay. So which is, so mu of x is equals to e raised to the integral of p of x dx. So e raised to, our p of x is negative 2 all over x dx. Okay, so as long as we can see dx over x here, so that is a natural logarithm. So that would make it e raised to negative 2 ln x. And then that would be equal to e raised to ln x raised to negative 2. And then this is the same as x raised to negative 2, or that is 1 all over x squared. So our integrating factor now is 1 all over x squared. And now, so we can compute, okay, or we can proceed, so with the general solution. So the formula would be our integrating factor. So multiply it to where it is linear. So this time around, since we transform it to be a an equation, so which is linear in v, so we will be multiplying it with v. Then that is equal to the integral of q of x, mu of x, dx. So mu of x, or sorry, our mu of x is 1 over x squared. Then multiply it with v. Our q of x is negative 2. Our mu of x is dx. Then, so this would become v over x squared is equals to, so to better integrate this one, so we move up the x squared, so negative 2, x raised to negative 2 dx. So to use power rule. So v over x squared then will be equal to negative 2. So multiply it with x raised to negative 2 will be x raised to negative 2 plus 1, which is negative 1 over negative 1. Then plus c. So simplifying this further, so v over x squared, so will be negative 2 divided with negative 1, that would be negative 2 or positive 2. And then divide it with, okay, so we move down x raised to negative 1 and then plus c. So this would be the general equations if it is linear in v. But then, so since we or we made some assumption about v, so remember that we made this assumption that v is equals to y raised to negative 2. So since v is equal to y raised to negative 2, so therefore, you have to take note of that, but v is y raised to negative 2 or 1 over y squared. So therefore, v is 1 over y squared divided with x squared. That is the same as 1 over x squared y squared. And it's equals to 2 all over x plus c. So if we don't want a fraction, so we multiply everything by x squared times y squared. Okay, so to cancel everything at the denominator. So leaving us to have 1, so equals to, so x squared y squared over x. So we'll retain a single x. So 2 times x, then y squared. Then plus c, x squared, y squared. And that would be the general solution. So 1 is equals to 2x y squared plus cx squared y squared. And that is how we do the Bernoulli's equation. So again, so our step, so we start with the q of x. So we transform everything as a function of x. So therefore, we eliminate y's. So by multiplying the entire equation by its reciprocal. And then once we are done, so we made some assumptions. So in here, so we assume, okay, so for the value of v, it could be any value, okay, so depending on how the equation goes. So v could be 1 over y cubed, okay? So v could be sine x, okay, so depending on the differential equation. So after making the substitution or the assumption, so we derive v with respect to x and we derive y with respect to x as well. And then, so we need to transform, okay, or substitute the dy over dx to whatever we have taken, okay, so from our assumption. And then afterwards, so once everything, or we have to clear, the last step is we have to clear the differential dv over dx with coefficient. Okay, so whether that will be a constant coefficient or a variable coefficient. And then afterwards, we were now able to transform it into a linear equation. So if it is a linear equation, then we follow the formula or the process in solving linear equations. So until the simplified general solution, so in this particular example, it's 1 is equals to 2xy squared plus cx squared y squared. Okay, so let's proceed with example number 2. Example number 2 is not on a standard form of Bernoulli's equation. As you can see here, so we have y prime is equals to 5y plus e raised to negative 2xy squared. So which are we going to move to the left or move or stay to the right? So remember, so this equation is Bernoulli's equation because of the presence of y, and then y raised to n, which is y squared. And in Bernoulli's equation, so we retain y raised to n at the right-hand side, and then the linear equation or the linear dependent variable should stay at the left-hand side of the equation. So in this case, this will become dy over dx, and then transpose 5y to minus 5y, then is equals to, so e raised to negative 2x times y squared. So that's transforming our equation, okay, so into the standard form of Bernoulli's equation. Okay, so we have y raised to n at the right-hand side of the equation. So remember, so we are transforming the equation to dv over dx plus p of x times v is equals to q of x. Okay. In this case, our supposedly for q of x, so we have e raised to negative 2x y squared. But because of the presence of the y squared, it's not linear. So therefore, we work out on that. So by multiplying everything by its inverse, so y raised to 2, so that would be y raised to negative 2. So doing so we'll have y raised to negative 2, so dy over dx, and minus 5, y raised to 1 times y raised to negative 2, so 1 minus 2 would be y raised to negative 1. And is equals to e raised to negative 2x. So y squared times y raised to negative 2 will be 1. So as you can see here, our q of x, so we're done with our first step at the right-hand side of the equation, so which is e raised to negative 2x so far. It might change. And then we proceed with our second step. So we want to make some assumption. So our assumption here, so we're going to let v, so we're not going to take negative 5y raised to negative 1. So we could just simply get a portion of it. So in this case, so our v should only be the variable. Okay, so do not include the constant, coefficient, nor the sign. So we just let v, okay, so to be equal to y raised to negative 1. That's just it. Okay, so do not include the sign nor the coefficient. And then we have dv, so we derive it with respect to x. So dv over dx, so will be equal to, so power rule, negative y raised to negative 1 minus 1, that's negative 2. And then we derive y with respect to x. And as you can see here, so the only difference is the negative sign. So multiplying both sides by negative, so that will lead to negative dv over dx is equals to y raised to negative 2 dy over dx. So we do now the substitution. So we do the substitution, okay, so to be done with the p of x. So y raised to negative 2 dy over dx, so for here, so that's the same as negative dv over dx. And then minus 5, so y raised to negative 1, it's the same as v. And then is equals to e raised to negative 2x. So now, we are done with the p of x times v. Okay? And lastly, so dv over dx should be positive. Okay? And without any coefficient. So we multiply everything by negative 1. Okay, so we multiply everything by negative 1, so giving us dv over dx plus 5v is equals to negative e raised to negative 2x. So now it's a linear equation. Our p of x is positive 5, and then our q of x is negative e raised to negative 2x. Negative e raised to negative 2x. And thus we can compute for our integrating factor, e raised to the integral of p of x dx. So which is e raised to the integral of 5 dx. Again, so in here it's just 5 dx. So integral of 5 dx is just 5x. So it's not necessary that ln should always be present here. So ln or natural logarithm, so will be the integral. Okay, so if the integrand is dx over x. But since the integrand is just dx, so the integral of dx is just x. So our integrating factor can be an exponential function. It's not always that we cancel out the exponential function. Okay? So it is possible that our function or our integrating factor is an exponential function. In this case, it's e raised to 5x. So thus, we proceed with our general solution working equation, so which is mu of x. So multiply it to linear in v, and then q of x, mu of x dx. So our mu of x is e raised to 5x, and then multiply it with v, is equals to our q of x is negative e raised to negative 2x, mu of x is e raised to 5x dx. Okay, so I'll start with v. So v e raised to 5x is equals to, so multiply the two, so both are exponential function with the same base, so but a different exponent. Okay, so we have a negative 2x and a 5x, so therefore we algebraically add the two, so giving us e raised to negative 2x plus 5x, so which is positive 3x dx. And thus, so we can now integrate this one. So our u here, so will be 3x. So we can just simply use the integral of exponential function. So our du will be 3 dx. As you can see here, it's only dx. So it is proper that we should have a neutralizing factor of 1/3. And thus, we have v e raised to 5x is equals to negative, so neutralizing factor of 1/3. And then the integral of eu du, it's eu. So which is e raised to 3x plus c. But then we have to go back that v, so we let v as y raised to negative 1, so which is the same as 1 over y. So substituting 1 over y from v, so giving us e raised to 5x, so v is 1 over y, or just simply e raised to 5x all over y. And then it's equals to negative 1 over 3 e raised to 3x plus c. Then we multiply both sides. So we have y and 3. So we can multiply it by 3y. So 3y over y, it's 3. So 3 e raised to 5x. And then 1/3 times 3y, it's just y. So negative y e raised to 3x. Then plus c times 3y. So it will just be cy. So since 3 would be absorbed by c, so leaving us to have a c only. And then multiply it with a variable y. So we can have this one. So 3 e raised to 5x equals to negative y e raised to 3x plus cy. Or if you want, so we can make it cy minus Okay, so it depends on how you express your final answer. But this will do. So 3e raised to 5x is equals to negative y e raised to 3x plus cy. Okay, so you may always go back with the solution. So if you want to absorb, okay, so how the process take over. So I'll proceed with example number 3. So example number 3, the difference of this example is that it has a rational exponent. Okay, it has a rational exponent. So both example number 1 and example number 2 do have integer exponents. So in this case, it's a rational exponent. How do we transform rational exponents? These are the one with square roots. Again, so we start with our original equation. So it's dy over dx. So the dependent variable is y. Independent variable is x. So we follow the same format. So dv over dx plus p of x times v is equals to q of x. So now, so looking at the differential or the Bernoulli's equation here, so we have y raised to 1/2 dy over dx plus y raised to 3 all over 2 is equals to 1. So the one on the right hand side is just 1. And what we should suppose to have there should be a function of x alone. Okay, so we can't see x there, we can't see y there. So therefore, we're not going to change anything from there. So we are already okay with our first step, okay, because there's no y there. Okay, so there's no y at the right hand side of the equation, so there's no need to eliminate. So currently our q of x is just 1. Okay, so next is we proceed with our second step, that is the assumption of the value of v. So let v, so our dependent variable is y, and we can see there y raised to 3 all over 2. So therefore our v would be y raised to 3 all over 2. So we derive it, so with respect to x, so y raised to 3 over 2, so 3 over 2, then y raised to 3 over 2 minus 1, that is 1/2. And then we derive y with respect to x. And then, so we only have y 1/2 dy over dx for our differential, and then we have a numerical coefficient of 3 over 2. So that's, to remove that, so we multiply it by 2/3. So therefore, 2 over 3 dv over dx is equals to y raised to 1/2 dy over dx. And we transform. So y raised to 1/2 is 2/3 dv over dx, and then plus y raised to 3 over 2 is v, and then is equal to 1. And we're done with our second step. So our last step is to free our differential from a coefficient. So that's, we multiply everything by the inverse, so which is 3 over 2. So leaving us to have dv over dx plus 3 over 2v is equals to 3 over 2. And from there, so we can get that both our p of x and q of x are equal to 3 over 2. So we proceed with the methods for linear equations. So by finding the integrating factor first, so e raised to p of x dx. So e raised to 3 over 2 dx. So again, so that's just a fraction. So we don't have dx over x, so therefore we don't have ln of x or ln of x. So it's just simply e raised to 3 over 2, the integral of dx, which is simply x. So our integrating factor is e raised to 3 all over 2x. So our general working equation then, so mu of x, so times v is equals to q of x, mu of x dx. Our mu of x is e raised to 3 over 2x, multiply it with v, is equals to, our q of x is 3 all over 2, and then e raised to 3 over 2x dx. So as you can see here, our u will now become 3 all over 2x. Our du is 3 all over 2 dx. And as you can see here, so we already have the 3 over 2 and we have the dx. So since the derivative of u is already present in our integrand, so there's no need for neutralizing factor. So this one will become v. So e raised to 3 all over 2x is equal to, it's just simply e raised to 3 all over 2x plus c. But we go back with our v. So we're in v is y raised to 3 all over 2. So we substitute. So v is y raised to 3 all over 2 times x. Oh, sorry, it's just y raised to 3 over 2. And then e raised to 3 over 2x is equals to e raised to 3 over 2x plus c. And that will be our general solution. Y raised to 3 over 2, e raised to 3 over 2x is equals to e raised to 3 over 2x plus c. Okay, so that's how we work out with rational exponents. Okay, so for our fourth example, so it's a trigo. Okay, so what makes it new? It's a trigo Bernoulli's equation with trigo functions. So again, so we can see here dy over dx. So since our dependent variable is y and then our independent is x, so we transform our dependent variable from y into v. Okay, so from y into v. So therefore, we follow the same general form. So which is dv over dx plus p of x times v is equals to q of x. And as you can see here, at the right-hand side of the equation, it contains both the function of x and the function of y. But what we want there is to have a function of x alone at the right-hand side of the equation. So therefore, what is in excess? In excess is the tangent y and sine y. The tangent y and sine y. So doing that, so giving us 1 over tangent y, sine y, and minus, so tangent y will be cancelled out, so leaving us to have 1 over x times sine y, then is equal to, so tangent y sine y will be cancelled out, leaving us to have 1 over x squared alone. Okay, so that's our q of x. For the meantime, it's 1 all over x squared. So now, we are going to transform this one to p of x times v. So I can rewrite this as 1 over tangent y, sine y, then minus, I'm going to separate the two as 1 over x, then multiplied it with 1 over sine y. So equals to 1 over x squared. And as you can see here, our dependent variable is y. So therefore, our assumption for our v then, so would be the function of y. So that is, so we let y, or we let v, so to be equivalent to 1 over sine y. So we let v to be equal to 1 over sine y. Okay, so that we could transform this one into a linear equation. And then, so before deriving, so I'll move up sine y, so to better derive it, so v would be sine y raised to negative 1. And then dv, so with respect to x, will be, so power rule. Actually, this will become chain rule. So negative, we bring down negative, and then sine y, negative 1 minus 1 will be negative 2. And then the derivative of sine y inside, so will be cosine y. And then we derive it with respect to x. So that's we have negative sine y raised to negative 2 cosine y. So we can use some identities here. But then let's bring it down first. So we'll have negative 1 all over. So sine y raised to negative 2, bring it down, it will become sine squared times y. Then multiply it with cosine y, dy over dx. But then we can separate, our objective here is, oh, I forgot. So we have the dy over dx here. So dy over dx. Our objective is, of course, we should get a 1 over tangent y sine y dy over dx. Okay? So we need to remove that one. So we can get that, okay, so from the derivative of our assumption. So dv over dx then, so will be equal to, so I can make sine squared y as a product of 2 sine y. So sine y, then the other one would be here. So dy over dx. So we can use some identities here. So negative 1 over sine y. Then cosine y over sine y, it's the same as cotangent y dy over dx. And similarly, so negative 1 over sine y. So cotangent y is also the inverse of tangent. So that would just be 1 over tangent y dy over dx. And thus our dv over dx just be simply, so negative 1 all over tangent y sine y dy over dx. Or simply, negative dv over dx is equals to 1 over tangent y sine y dy over dx. So which is exactly as this one. So therefore, we can now change that. So 1 over tangent y sine y dy over dx, it's the same as negative dv over dx. Then minus 1 over x. And then 1 over sine y is v is equal to 1 over x squared. And lastly, we remove the negative sign. So for the differential, so by multiplying everything by negative 1, so dv over dx plus 1 over x times v is equals to negative 1 over x squared. So our p of x then is 1 over x, and our q of x is negative 1 over x squared. So computing for the integrating factor mu of x, so e raised to p of x dx, so e raised to 1 over x dx, or simply dx over x, so which is ln x. And thus we have our integrating factor to be x. Our working equation now, mu of x times v is equals to integral of q of x mu of x dx. So mu of x is x times v. Q of x is negative 1 over x squared. Then multiply it with mu of x, which is x, times dx. I'm going to interchange the two. So vx will be equal to, so negative, so x over x squared is 1 over x, or just simply dx over x. So thus, vx is equals to negative dx over x is just ln x plus c. But then we have the value of v, so which is 1 over sine y. So, but v is 1 over sine y. Or if you want, so we can make it cosecant y. So, simply put, so this is the same as, so v is cosecant y, so it's just x cosecant y is equals to negative ln x plus c. And that's our example number 4. So Bernoulli's equation with a trigo function. So let's have our last example. So last example is not on the standard form of a Bernoulli's equation, but this is a Bernoulli's equation which can only be realized that it's Bernoulli's equation. So once we manipulated the given differential equation. Again, so in dealing with this one, so if our assumption here so to be a Bernoulli's equation, so we have to transform this one first into dx over dy or dy over dx. Okay. But the thing here is there are two dy's. Okay. So there are two dy's, so which are available on the differential equation. So that's our first approach here, is to combine the two. Okay, so combine the two. So combining it, it will lead to 3x squared y squared minus 3x squared dx, and then plus, so we'll have x cubed y minus y squared minus 1 raised to 3 all over 2, and then multiply it with dy is equal to 0. So x cubed y minus y squared minus 1 raised to 3 all over 2 dy is equals to 0. And then, so there are two things that we can do here. So it's either we're going to make it dx over dy or dy over dx. But then, there are two terms involved. Okay, so there are two terms here. So this is the first term, this is the second term. This is the first term, this is the second term. Okay. But looking at the first one, okay, so the function which is multiplied with dx, so there's something that is common there. Okay, so we can see that 3x squared is common. So I can factor out 3x squared first. And that will lead us to y squared, then minus 1 dx. So by factoring it out, so by factoring out 3x squared, so leaving us to have 3x squared multiplied with y squared minus 1 dx. And then plus, so we have x cubed y minus y squared minus 1 raised to 3 all over 2, then multiply it with dy is equals to 0. So again, so in deciding, so whether we're going to divide or we're going to make it dx over dy or dy over dx, it depends on what we are multiplying. Let's say we have this one. So let's say I have y squared plus 1 over y, and then the other one is y all over y squared plus 1. So remember that this one can be separated into two as the same as y squared all over y, and then the other one is plus 1 all over y. So we separated the given expression into y squared over y plus y over 1. But then for this particular expression, y over y squared plus 1, this is not equal to y over y squared plus y over 1. Okay? So it violates properties in algebra. It's not equal. So therefore, in deciding, so whether we're going to divide it with the function involving dx or the function involving dy, so we have to decide so which is a function which is considered as a single term only. So in this case, there are two terms here. This is the first term, then minus, so that's the second term. Unlike for the function multiplied with dx, so it's just a single term. Okay, so kasi product of two functions is still considered as a single term. So thus, the advisable, okay, so differential here would be dx over dy. So we multiply, so our it should be dx over dy for our differential. So meaning dy will move down. So therefore, so what is multiplied with dy, so we'll retain there as x cubed y minus y squared minus 1 raised to 3 halves. And then the function which is multiplied with dy, so which is this one, so we'll move down. So giving us 3x squared, then y squared minus 1 is equal to 0. So why did we do that? It's because we want to separate this one into two terms. Because our differential equation, so in Bernoulli's form, contains the p of x and the p of or q of x. But in here, since our dependent variable is x, okay, and our independent variable is y, so therefore, our new dependent variable v should be derived so with respect to y this time. Okay, so it will be dv over dy. So since our dependent variable is no longer y, it's x. So that makes it dv over dy, so plus p of y, then times v is equals to q of y. Okay, so since our independent variable this time it's y, it's no longer x. So we separate the two. So dx over dy, so our first term is x cubed times y. So divide it with the denominator of 3x squared, y squared minus 1. Then minus our second term, so which is y squared minus 1 raised to 3 over 2, divided with 3x squared, y squared minus 1 is equal to 0. So now, we have dx over dy, so plus, so this one would become x cubed, x squared, so 3 minus 2, so we still have 1 there. And then in here, so we have y squared minus 1, y squared minus 1. So this is 1. So 3 halves minus 1, that is still, we still have 1 half at the numerator. So that's giving us x times y divided with 3 times y squared minus 1. And then minus y squared minus 1 raised to 1 half, and divided with 3x squared is equal to 0. So since we want this one so to be linear in v, so we can transpose the y squared minus 1 raised to 1 half at the right hand side. So because this is linear in x, so this one makes it linear in x. Okay. So this would become dx over dy, and then plus y over 3 times y squared minus 1, then multiply it with x. So this is linear in, we're assuming that it should be linear in x. Okay, so because of the dependent variable, then it's equals to y squared minus 1 raised to 1 half divided with 3x squared. So going back with our original, or we are transforming it into this format. So we start with qy. So meaning our function should be a qy should be a y function alone. So thus, at the right hand side of the equation, we are in excess of 3x squared. So to make a qy at the right hand side. So this would make it 3x squared. So dx over dy, and then plus 3 and 3 will be cancelled out. So leaving us to have y all over y squared minus 1. Then x times x squared is x cubed is equal to, so 3x squared will be cancelled out. So y squared minus 1 raised to 1 half. So that's we're done with our q of y. So next is we assume for the value of v. So since this dependent variable is x, so we let v so to be equivalent to x cubed. So this time around, so we derive this one with respect to y. Okay. So since our independent variable is y. So dv over dx will be 3x squared and then dx over dy. And as you can see here, so they are exactly the same. So 3x squared dx over dy is the same as dv over dy. And plus y over y squared minus 1. So x cubed is v. Then is equal to y squared minus 1 raised to 1 half. And from there, so we can identify that our p of y is y over y squared minus 1. And then our q of y is y squared minus 1 raised to 1 half. So our integrating factor mu of y then, so would be e raised to the integral of p of y dy. So e raised to the integral of y over y squared minus 1 dy. So in here, our u will be y squared minus 1. Our d would be 2y dy. So what we only have is just y dy. So therefore, we have a neutralizing factor of 1 half. And that's giving us e raised to 1 half. And then that is ln of y squared minus 1. Or e raised to ln y squared minus 1 raised to 1 half. Or just simply y squared minus 1 raised to 1 half. Then going to our equation, so mu of y, so linear in v, q of y, mu of y, dy. So our mu of y is y squared minus 1 raised to 1 half times v. Q of y is this, so which is still y squared minus 1 raised to 1 half. It's the same thing as with mu y, so y squared minus 1 raised to 1 half times dy. So y squared minus 1 raised to 1 half times v. So we have the same base, so which is y squared minus 1. And then so we add the exponent. So y squared minus 1, so 1 half times 1 half, or 1 half plus 1 half, that would just be 1. Or that's just it. And then we integrate. So y squared minus 1 raised to 1 half times v will be, so power rule, so y cubed over 3 minus y plus c. But what is our assumption with v? So v is x cubed. So that's giving us, I'll start with x cubed, then y squared minus 1 raised to 1 half is equals to y cubed over 3 minus y is equals to c. And multiplying everything by 3, so finally giving us 3x cubed y squared minus 1 raised to 1 half is equals to y cubed minus 3y, sorry, that should be plus c. And this will be our final solution. Okay, the final general solution. And that is all about Bernoulli's equation. The activity, okay, computational activity would still be individual for the meantime. And then it's already activated due on Monday. So you can do it until Monday. But if you have free time, so you can start answering your activity. And that will be all. Good day.